Good afternoon, everybody. So I realize I am the speaker standing between you and the lunch, so I'll try to be on time. So what I want to tell you today is our latest unpublished experiments where we use strong terahertz pulses on an antiferromagnet. And what we do is, after we kick this thing with a giant terahertz pulse, long-lived magnetization happens. So before I actually tell you about our results, let me motivate this work a little bit. So we know that in general, the way to think about phase transitions, at high temperature you have rather featureless free energy, and then when you cool down, there are all these minimas, and the system gravitates towards the global minima. Now, in this community, we have had multiple examples where you can actually shine an optical pulse, and what you do is you transiently melt this, low energy minimums, and then you go into an excited free energy surface. And then what can happen is that the system can get stuck in one of these local minimas, and then we call this a light-induced phase transition. So there's multiple examples of this, and this is great in general, but there are some challenges with this approach. And then I'll just put two of them here. So number one is that typically in these experiments, you're kicking with an optical pulse that has very large flumes, and as a result, you're heating up the electrons. There's a lot of heating that is being introduced to the system, so this is a little bit uncontrolled in a sense. And the other thing is that this thing generally leaves quite a bit short time, so picoseconds, tens of picoseconds. So what you want to do is you want to do it in a bit more controlled way, number one, and number two, if possible, you want to make it live longer, right? So that's kind of the two challenges that I'm going to try to address in my talk. So now, one way you could do this is you can basically look at systems where there's already a strong coupling between different degrees of freedom, between electrons and structure, or magnetism and structure, etc. And then the idea is that if there's already these couplings, here, well, you can actually, let's say you want to induce a magnetic phase transition, and you don't really know how to couple to the magnetism with light. What you could do is you could actually couple to the structure and let the material do the work through this coupling. And then one way to illustrate this is that, you could basically excite a phonon mode, let's say, and if you can kick this thing into very high amplitude, you can go through and then realize a magnetic phase transition. So let me emphasize that this is not my idea. It's actually Andrea and his coworkers who actually pioneered this field. Maybe you can term it as basically inducing a phase transition through a mode selective excitation. So let me show you an example of this. And then the material that I'm going to do this on is called iron phosphor trisulfide. I'm going to give you a bit of a background on this. And then I will explain our experimental technique, high field terahertz palm optical probe. And then I'll tell you what we observed that's actually interesting. So let's begin with the material. This is a layered antiferromagnet. It basically brings to this broader class where you have a metal like iron, nickel, manganese, and then this thing can be a sulfur or selenium. The general structure is like layered like this, and then this is the iron here in our case is hexagonal in plane, and between the two planes they are shifted a little bit, so it has a monoclinic structure. So what's important here is these exchange interactions, J1, J2, and J3, and the relative magnitude of these basically dictates where you are in the phase diagram. So, if you do a simple calculation, this is done by our theory colleagues, you could see that depending on the relative magnitude of these J1, J2, and J3, you could basically go into one of these exciting, yes?
Is all in the same plane, or does this picture,
this one is all in the same plane, J1, J2, J3. These are all, yes.
And layers are sort of, are they correlated, or they?
They are correlated. So I'll show you. In this particular case, in iron phosphor trisulfide, it happens to be in this zigzag phase in which along the chain it's ferromagnetically coupled and the spins are up. So spins are perpendicular to the plane in this material. In the neighboring chain, it's down. So up, down, up, down. And coming back to your question, in the neighboring layer, it's the other way around. So this is an up chain, this is a down chain, etc. So this thing is an antiferromagnet. It's totally compensated. There is no net magnetization in this system.
Are these rising light spins or?
Yes.
Rising?
Yes. So before I actually show you our results, let me actually tell you some equilibrium characterization of this system. So people have done Raman, for example, and when you do Raman, what you find is that when you cool below Néel temperature, a bunch of new phonon modes appear. So just the existence of these phonon modes already a good signature that there is strong spin lattice coupling, because what's really happening is that because of this antiferromagnetism, the unit cell is doubled, and what you're doing is you're zone folding the phonon modes, and that's what we're observing here. Now, you could see that besides these phonon modes, there's also this thing here which softens, and what this is a magnon, right? So if you take this magnon, and if you actually apply magnetic field, you could split this thing. This is a doubly degenerate magnon, and what you're seeing here is that just Zeeman splitting between the two degenerate modes. Now, further on this, this is I'm showing basically the same data by a different group here. These are the phonon modes, and this is the magnon. And as you apply the field up to about 10 Tesla, you can nicely see that the magnon mode is splitting into two. If you crank up this field, you see actually something quite interesting, that this phonon mode, basically this magnon mode, anti-crosses with this phonon mode, right? So this is yet another, great signature that there is strong spin lattice coupling. Now, this system is inversion symmetric, and in an inversion symmetric material, phonon modes are either Raman active or infrared active, but not both, okay? So this is Raman, but now if you try infrared spectroscopy, you actually also observe this phonon, all right? So this shouldn't be allowed. This is a Raman active mode, but you are seeing it here at this field value. The reason why you are seeing it is because these things are mixed. So this phonon is not really just a phonon, it's actually a mixture of a phonon and a magnon. And the way you were able to see this in this direct infrared absorption is because basically it's magnetic dipole absorption, right? So you could kick the magnon with magnetic dipole, and as a result, you can excite this phonon through that mechanism as well. So everything that I said so far, I'm just trying to emphasize that there's high spin lattice coupling in this material as observed by the equilibrium probe.
Sorry, but for lower field, you don't see the peaks in transmission.
So like these, these, yes. So that's right, and there's two reasons for that. How much there's mixing between phonons and magnons varies depending on which phonon mode you're looking at.
The mixing is maximum where the two near to the crossing point.
Yeah, I think the observation is maximum near the crossing point, but even at zero field, there's considerable mixing. Yes.
What about this lowest feature here? So what's that guy? The lowest one you highlight in red that's seen in the IR. So it looks like a phonon.
This one right here?
Yeah.
Sorry. Yeah.
But it's seen, yeah. Yep.
This is the P2 phonon. This is exactly this guy. Yeah, but as I was saying, the coupling between this one and the magnon is not as strong as this one and this one.
So you're picking up an itty bit of it.
Yes.
You're coupling to the magnon.
Yes, indeed. All right. So now the question is this: given that there is very large spin lattice coupling, could we, use this thing and then, manipulate magnetism by coupling to these modes? So this brings me to our experimental technique. So what are we going to do? We're going to come with a terahertz pulse, excite this thing. The pulse has a significant bandwidth that covers these modes, and then we're going to try to observe what happens to the magnetism. So this is the experiment. Our terahertz pulse is rather high bandwidth. It goes up to 6 terahertz or so. And then the field amplitude it goes up to about 300 kilovolts per centimeter. And then after we kick the material with terahertz, we're going to use an optical pulse. And then by analyzing the polarization of this optical pulse, then we are going to try to make conclusions about the magnetic state of the sample. So let me do this. So basically, the two different things that we are going to measure is either polarization rotation of this pulse, okay, and then that basically tells us about the difference between A and B axis in the imaginary part, the index of refraction differences, or we're going to look at ellipticity change of this optical pulse, and that basically is really more related to the real part, right? And that you know, I don't want to go into the experimental details, but that you actually do by using a quarter wave plate or a half wave plate here when you do the detection. Very good. So now, before I actually show you the pump probe, let me take the pump out and just show you the probe, right? So what I'm doing here, there's no terahertz pump here. I'm just sending an optical probe. I just want to understand, as a function of temperature, what do I see, right? So the first thing that I'm plotting here is the polarization rotation. So we're just sending a linearly polarized optical pulse, and this thing goes through the material, and I'm plotting how much polarization rotation that we see. So what you see here is that right at the Néel temperature, so there's no signal above the Néel temperature, but right at the Néel temperature, there's a large signal that kicks on. And we're not the first ones to see this. People have actually done this in reflection. You could do exactly the same experiment, and you see that there's indeed a large rotation that you see. So the way you understand this, this is not a linear magneto-optical effect. This is not allowed. Linear effects shouldn't be allowed in this symmetry class. So what this is actually a second order effect. But as a result, what you're really picking, you are picking an anisotropy, some linear dichroism along this chain direction and perpendicular to the chain direction. So this signal that you're seeing is basically proportional to the antiferromagnetic order parameter. And there's a nice way of detecting it optically. Yes.
When you say imaginary part of N, you mean imaginary part of an A minus and B.
Yes, exactly. That's right. Right. So this is at some angle. This is not along one of the axes. We are seeing the. All right. So this is one of the channels. So right now I'm just showing you what we see when we do take the pump out of the picture. So and then in the second channel, where we detect the ellipticity change of this optical pulse, you know, we also see an onset around T Néel, but we also have signal above T Néel. The way we interpret this is that this channel is sensitive to the critical fluctuations. You know, so different from this guy, we also have some signal above T Néel as well. Okay. So that's what we see in you know, static experiments. You know, now let's actually bring our pulse. So this is our terahertz pulse, and if you take a Fourier transform, this is our spectrum. As I said, it goes up to about 6 terahertz, and these are the phonon modes that I showed you in this Raman experiment. This red one here is the magnon. So the nice thing is that it covers most of these guys. So what we expect is that, you know, this is going to do something to this, right? So now let me show you the data at 10 Kelvin. So what I'm plotting here is ellipticity change of the optical probe after we kick it with the terahertz pulse. So there's two things we see here. Number one is all these mode oscillations that we kind of expect given our bandwidth. And number two is that there's also this offset a little bit around 0, right? So this part here is basically optical Kerr effect. When the light is there, terahertz light is there, we see some change. We're not going to focus on this. Rather, we're just going to analyze these modes that we see after the pulse. So what I can do is I can basically take a Fourier transform of this segment of my signal, and that's right here. So you know, what we observe is that we basically observe all of these modes. You know, they are very sharp. So this one right here is the magnon, okay? And then these other phonons, they are also there, right? And we even, you know, this one is very, very strong. You might say this is out of your bandwidth. How on earth you are observing this? We are observing it because of the 2 photon type of. Well, it could be 2 photon. It could be a photon plus a magnon. You know, photon plus a, you know, a phonon. All of those are possible, but this is nonlinearly excited. That's what I'm saying. All right. So now, how do I know that it's nonlinearly excited? So one way to tell is, I can look at each one of these modes and I can plot how the amplitude of these modes changes as a function of the terahertz electric field. So here, for example, if I start with the magnon, I see that it's linear, and that's kind of what you expect. This is magnetic dipole absorption, right? So it's linear. If I look at this phonon right here, it's quadratic. It makes sense because my probe is optical. It's a Raman probe. I'm not, even though I am able to excite infrared modes, I'm not able to probe them because I'm probing with optical. It's a Raman probe. And then, therefore, I cannot directly excite this phonon with my terahertz. Instead, I can excite it, either like a some frequency generation or a Raman-like process. Interestingly, if you look at right here, this mode here, which people in the literature, because of its strong coupling to the magnon, they call it a magnon polaron. You actually, you see more like a saturation-like thing, but instead, this is really not a saturation, but it's a linear superposition of these. This is like this minus this or something, right? In fact, we can change the phase of the terahertz, and then we can make it go that way as well, right? So in summary, the way I am exciting the magnon is through magnetic dipole absorption. This phonon is excited non-linearly. It could be a 2-photon or a Raman or any other 2-photon or like a process. And whereas this mode here next to the magnon is more like interference of these two mechanisms. Okay, so far so good, but I still haven't showed you what's exciting. Now, let's look at the temperature dependence. So this data that I showed you right here, this was at 10 Kelvin. Let's actually see how does that change it as a function of temperature. So here again, that 10 Kelvin data. As I warm up the temperature, Neal temperature is around here, 118 Kelvin. What you see is that above T Neal, you lose many of the oscillations. Some still remain, but most of them are gone. It's kind of consistent with that Raman data that showed that all the zone folded phonon modes go away at Neal temperature. So what I could do is I could just take a Fourier transform and then show you that as a function of temperature. And here again, so this is the Neal temperature. These are the different modes that we observe. And then you can see that here's the magnon. You can see nicely that it softens towards T Neal. So that's the magnon. All the other phonons, they lose their intensity, but they don't really change their frequency. Now, one interesting thing here is this thing here. So right around T Neal, in Fourier transform, I start to pick some DC signal here. So what is that? So you can fool yourself with Fourier transform. So the best way is actually to look back at the time traces. So let's do that. So when I look at what's happening around T Neal, I realize that my signal does not go back to equilibrium, right? Well, there's every other trace, either below or above T Neal, it relaxes back, right? So I go up, and then these oscillations happens around 0, but here it doesn't, right? Well, first I say, well, this is only 15 picosecond, go 10 times longer to 200 picosecond, and it should go back. It doesn't. So here, this is around T Neal, and what I'm plotting here is the polarization rotation and ellipticity change. We kick with the terahertz pulse, and then now we're looking up to 200 picosecond, and what we are seeing is that this signal is still rising, right? So look at this. So there's some long-lived signal around T Neal that I'm picking up with these two channels. Now, what I could do, I can try to look at the temperature dependence of this. Let's park here and then plot the temperature dependence of this offset. Now, what we are seeing is that for the polarization rotation channel, there's a very sharp onset, and then it's maximized around T Neal, and then it comes down. For the ellipticity change, it looks like almost like a true divergence around T Neal. It's kind of symmetric, it's a bit below and above T Neal. So now the remainder of this talk, we're going to try to understand this signal. Now let me actually think about what this could be. So if I look here, I know that the static probe of this, remember, if I didn't have the pump, if I just had the probe, we are basically probing this L, right? So L comes on and then this. So imagine that my terahertz pump, what it was really doing, it was, this is not the case, but let's say it was just heating up by a tiny bit amount, right? So delta T, right? Now, what you would expect is that you would, of course, see a signal delta linear dichroism, but then you can check this, and then the way you could check it is that you can integrate this signal in temperature, and if the integrated signal, overlaps with this, then so indeed in this case it does seem like it's overlapping, right? Now, even though we have other experimental evidence that this is not purely thermal, but a simple thermal interpretation might also do well here. Okay. Now, if you try the same thing on this channel, it doesn't work, right? So the integrated signal does not overlap with the static signal. So there is actually definitely more going on here. So even here, I mean, you can imagine that my terahertz is not exciting any of the electronic things. So the heating introduces really, really minimal. But what it is doing, though, it is actually decreasing L, and that's what we are picking here. So then what else can this be? All right. So at the end of the day, what we are seeing is a change in ellipticity. All right. So this can come from two things. One is linear birefringence, simply A and B axis. They have different index of refractions in the real part. But there's another way, and that is if you had circular dichroism, and that would be a totally different thing, right? Now, let's remember, there is no static circular dichroism. This is a totally compensated antiferromagnet. We also checked this. We tried to measure circular dichroism. It doesn't exist. But then the question is there Terahertz-induced circular dichroism? We can experimentally check this by doing this experiment. We send a terahertz pulse, and this time we check the response of a right circularly polarized probe and a left circularly polarized probe. And then when you do that experiment, indeed, right around T-nil, you find a big difference between the right circularly polarized and left circularly polarized. In fact, if you actually plot the temperature dependence of the circular dichroism, this exactly agrees with the ellipticity change. So what we believe is that the ellipticity change that we see is indeed coming from the circular dichroism, all right? And the moment you see a circular dichroism, it can come from two things. Either there's some chiral thing going on in your sample, which is not the case in this one. It's not chiral. None of the phonon modes we are looking at chiral, or it can come from magnetism. So, the one interpretation, therefore, is that what we are really doing, because we see this circular dichroism, the terahertz pulse must be inducing some magnetism in the sample, and this is somehow maximized when you are around T-nil. Now, the other thing is that this thing is very, it takes quite a bit to rise. It takes some time for it to reach the maximum, and the decay time is also very, very long. We even didn't, talk about it just yet. So if you plot this rise time, that also shows some kind of a divergence. And then you can fit all of these with exponents that kind of consistent with like a 3D Ising model kind of things. So then initial question is, this thing eventually should come down. How long is the decay? So the decay is so long that, within one pulse, we can't really measure it. Our laser has a 1 kilohertz repetition rate. But what we could do is we can use the fact that right before the pulse is essentially like a 1 millisecond delay time, right? I was, zeroing all these curves before time zero, but if I stop doing that, you actually see that there is indeed a signal before time zero, and that around T-nil. When you go away from T-nil, that goes to zero. And the reason why there's a signal is because this thing still didn't go to zero after 1 millisecond. In fact, we can do tricks where we can measure it in the successive pulses at 2, 3, 4 milliseconds. And then that actually gives you can easily model this and you can get a lifetime. What we find is that this thing lives about 2 milliseconds, right? So the lifetime of this state that is made by the terahertz pulse is on the order of 2 milliseconds. So what is this? Microscopically, how is it that you can actually induce a magnetization? So there's one key question, which is that I'm putting a giant terahertz pulse that has, the magnetic field is about 0.1 Tesla. So it could be that somehow this big field could be inducing this, number one. Number two, it could be these excitations that I made by the field could be resulting in this, right? So how do I tell? Is it the field or is it the excitation? So here I'm showing you in our lab, we had this broadband terahertz, and then we see this long-lived signal. Now, the experiment that we are going to do, we're going to use another terahertz source, which has a narrow bandwidth. This was done in an organic crystal of DNA. If you generate terahertz with lithium niobate, so this was done in collaboration, this part was done in collaboration with Keith. Lithium niobate has even a stronger terahertz than ours, but it has a very small bandwidth that it doesn't cover any of these excitations, right? And as a result, we lose this long-lived signal. So very clear answer. It's not the field, it's the excitations that you make with the field. Okay, so then the question is, how do these excitations lead to net magnetization, right? So for this, we needed to talk to smarter people than us, theorists. We were collaborating with Angel and Emil for this work. So what they did was the following. They looked at these phonon modes that we are seeing in our signal. I'm just putting these three modes that are closest to the magnon here. This is what the oscillations look like. So for example, the 2.62 terahertz is just doing this, up and down out of the plane. 3.26 terahertz, this is the one that's closest to the magnon, most strongly coupled. And this has this anisotropic mode in plane oscillation. And this is symmetric in plane, right? So then you ask yourself, what would happen when you excite these modes? Now, then you realize if you freeze these phonon coordinates at this point in time, you see that this bond length is actually longer than this one. So as a result, what's going to happen is that you're going to decrease the exchange interaction between these two atoms, but increase the one between these two, because this is getting closer, this is getting farther away. In fact, what they can do, they can actually calculate how, from first principles, how should these exchange interactions depend on these phonon coordinates. So you can see that for this particular mode, what you're really doing is you're weakening this ferromagnetic chain that's pointing up, but you are strengthening this one that's pointing down, right? And you can kind of guess that there should be a difference between. Initially, they were compensating each other, but then when you do this, they won't anymore, right?
Excuse me, Nuh,
yes.
but so if this is linear in Q, then at linear order, the effect should go to zero, right? There needs to be some rectification.
Yes.
Okay, you're getting there.
Yes, I'm getting there. Yes. You know well to okay. Yes, as Andrea said, if everything was going around like this, it would just average out to zero. Phonon Q positive, Q negative, it's just sum up to zero, right? So nonlinear excitation is critical, right? If you were not excited, and indeed these are Raman active phonons, and not exciting these linearly. So if you're exciting them with E squared, not with E, then there will be a net displacement of this phonon. So if there's a net displacement of this phonon, then you can understand that this will be static. It won't be averaging out to zero. So now also this was just an intuitive thing, and they did spin Monte Carlo, and in fact they find that for this particular phonon mode there's net magnetization. And then one way to understand why, just to be a bit more quantitative, why this is the one that actually gives you net magnetization is the following. So when you think about how this is going to modify this Hamiltonian, you basically have this extra term that's coming because this exchange interaction between S2 and S3, you're going to get this extra term because J has changed, right? Because of this Q, right? And this will be the opposite sign of this guy because this J got bigger, this J got smaller, right? Now, when you write this term, and then when you actually, relate these, this expression here to antiferromagnetic and ferromagnetic order parameters, you can rewrite this term, and this is basically all this is just a coupling term between L and M, okay? And that's actually proportional to the phonon coordinate. So now, because now you have this coupling term in the Hamiltonian, if you were to write a free energy, besides the L and M, you should also include this coupling term and the phonon coordinate. So the long story short, when you actually look at the free energy diagram, what you find is that the global minima happens not at m equals to 0, but at a finite q and a finite m. Okay, so this is, even in static, the system prefers to be distorted along this phonon coordinate and have a net magnetization. But when you kick this nonlinearly, such that the phonon is excited and there's a net displacement of the phonon, you go to a specific q, and for that given q, there is actually a net magnetization. Okay, and that's what we are picking up in our system. And relaxation of that magnetization back really is, around t nil is slowed down because it basically relies on, fluctuations of L, right? In fact, if you solve for the global minima of M, it's proportional to the L squared, not L itself, but L squared. And kind of you can understand why around t nil this should be very, very slow, number one. Number two, you can also understand, even though there's L itself is 0 above t nil, L squared is not. There are still fluctuations, and you can still see this magnetization above t nil. So let me summarize. What I've showed you in the experiment is that with this, terahertz pump optical probe type of experiment, we can see all these modes very nicely. We see a long-lived metastable magnetization around t nil, and we understand it based on basically a nonlinear excitation of this particular phonon mode that gives us net magnetization. So with this, yes,
I got confused. Can you just so if I go deep inside the antiferromagnet,
yes,
don't pump anything.
Yes.
Doesn't this mean that there is an equilibrium distortion and an equilibrium magnetization? I mean, it's just a couple.
Very good. So if yes, so no, that's good. So now, yes, indeed, the equilibrium point is not at q equals to 0 and m is equal to 0. The system does prefer to be distorted along q and along m, but so then the question is, why doesn't this happen in equilibrium? So it's a little bit like the example of strontium titanate. You can think about two minimas here, and then if the barrier in between the two minima is actually small enough, the system doesn't really go into one of these minimas. It's kind of in a superposition of the two. So there's really no net magnetization, even though there are two minimas. But when you derive the system at a particular q, that minima gets very deep. Yeah, thank you.
Okay, but that also means that if that's all there is, go to low enough temperatures, there will be additional order.
STO, it doesn't happen.
It doesn't happen in STO.
I see there's quantum terms there.
Yes.
Okay. Right.
So and that's why you see this on the orbital, you see these fluctuations close to L. You
Yes.
saw these precursor
Exactly.
fluctuations, yeah.
But then I'm still not, okay, so it fluctuates in equilibrium, but then you are saying you're pushing it and somehow then it gets stuck in one of them.
Yes, and also for a finite, so when we drive it to a net q, that means one of those minima get actually deeper than the other one. Okay, so this thing that I'm showing basically is right. So when you actually drive it to a net q with the phonon, and then if you just plot it as a function of m, the free energy as a function of m, the two minimas are not equivalent anymore. One of them is actually lower than the other one. So the system gets stuck there until, no, it's because of this nonlinear driving, there's net displacement of the cube. Okay, I should have done a better job of showing.
You're saying there is something which forces our Q to acquire non-zero value.
Yes, exactly. So the way you are driving it, because of this nonlinear excitation, it goes like e squared. Yes, Andre?
So I'm going to say something that also, we have the same problem.
Okay.
I can live with a long lifetime to come down.
Yes.
Because you need, maybe there's a weak spin orbit and then it takes forever to lose angular moment. But also, we also observe in cobalt fluoride, where we see something similar, that the rise time is longer than the lifetime of the phonon. Your rise time is too slow for your mechanism. And that's the same problem that we have that I never understood, right? Your phonon, your rectified phonon is going to relax in 10 picosecond in a good day.
Okay.
Your rise time is 30, 40 picoseconds.
True.
Yeah. Did you ever understand this?
Not exactly. I understand what your question is. So the question is, even after the phonon is gone, why is it that the system
It keeps on growing. The magnetization keeps on growing after the phonon is gone.
Right. So I mean, understanding decay is easier than the rise time, correct?
Decay, I'm good.
Yes. Yes.
Decay, no
Yeah.
problem.
So somehow also the rise time is. It sounds like we rely on the fluctuations now, but there's a slight disagreement. Your question, you said cobalt fluoride.
We worked on cobalt fluoride.
I know. But this is different, right? In
Yeah.
fact, let me see if I have it.
But anyways, no, so forget
Here's
cobalt fluoride.
Okay. So there was a beautiful work that Andrea did on cobalt fluoride. Yeah. Perfect. But there the mechanism was piezomagnetism, right? Which is that when you apply strain, it's a totally compensating antiferromagnet, but then you can actually, make one of the moments smaller or larger than the other one, so you get ferrimagnetism, right? And then this is perfectly fine with cobalt fluoride because you could the piezomagnetism is symmetry allowed, but in our system it's actually not. So just the mechanisms are different.
Right.
Yeah.
But in both cases, the rise times are too long.
Okay.
We never understood the rise time, actually.
Yes. I think there's definitely more to be done.
Right.
Yes. So with this, I want to leave you with a picture of my dear.
Further question, maybe it separates.
One quick question, did I miss, you said it's easier to understand the case, but did I see decays?
I mean, I at least show you. So I mean, we know the decay time, right? I showed you that we can estimate it by this thing here, right? And then we know it's around 2 years.
One question though, and maybe I misunderstood. You have there seems to be an asymmetry between right and left pumping. Is that right?
Right and left pumping.
Did you show that it was sensitive to terahertz right, but not to left?
I mean, probing, you mean? So this is the terahertz, linearly polarized terahertz pumping, and then I am probing with the right circularly polarized and left circularly.
And then, so then the question is,
So this is how I know
what sets my question remains though, what sets the sign of this effect then?
Very good question. So it's set by the coupling. So let's say this phonon is driven nonlinearly proportional to E squared, but there's a coupling term here, G times E squared. So that sign of that G really what sets the sign of the effect. So in other words, it's material specific.
Sensitive to right or left, in other words, right? So there's some, you pump it with linear,
yes,
but it's more sensitive to right or left afterwards.
Yes,
so
that's right. Well, I mean, this is, but if I just translate your question, you pump it with linear, but we only see magnetization pointing up, not down, right? And then that is set by the material specific coupling parameters. So in terms of, because the driving term is proportional to E squared, it could be a positive E squared or negative E squared. That determines if you have magnetization up or down.
This is set by the high temperature normal crystal symmetry. There's a polar vector that's out of the plane.
I think that's one way, but it also depends how this phonon is nonlinearly excited. If it is, just simple 2 photon like E squared, or it could also happen through a different phonon. But in any case, it depends on the crystal itself. Yes.
Yes, I'm still puzzled by the story with the landscape. So you're saying in equilibrium, I have 2 minima with small cube.
Yes.
And you're saying I'm driving and somewhere I find another minimum at larger cube for the system can be stuck. So somehow you're hiding under the rug that there is a profile in which there are some metastable minimum. You did not show us the part of free energy.
I didn't.
That would actually have those local minima.
Okay, so I mean, I think you can take some cuts from the free energy. So let me actually see if I have it here. Okay, so like here, for example, another way of looking at this. So for a fixed Q, so there are different ways you can minimize this, right? So I can do the following. I can just, fix the Q, just like my drive that sets the Q, and then ask if I minimize this thing under this condition, what is the M that I get? Okay, and that's this guy. Okay,
that's not enough to be stuck there.
I know. So, but then, what you really should do is you actually should solve this and minimize it, and this is the true minimum. Okay, So the system is going to go there initially, but then it's going to relax here. Okay. So now what I was trying to say is that for a fixed Q, okay, so you could see that this side is definitely not symmetric as this side. So the system prefers this right here. But eventually it's going to have to go here because that's the true minimum.
But again, I think the same question, like some electric field is moving Q like symmetrically between positive or negative, or you are saying that actual electric field really gives me bias in Q.
Electric field does give you bias because it's not the electric, it's E squared. It's just one side.
Actually, can I?
Yes.
Yeah, I think,
Luca and then Vadim.
yeah, so you extracted this critical exponent or some kind of critical exponent when the time scale diverges. Does it match some kind of critical slowing
Yes,
down?
it does match general universal class of 3D Ising systems. Yeah.
Can I come, I'm still hung up. I just want to follow up on Peter's question about signs.
Mhm.
So if you say that the basic coupling is that one, G, L, M, Q.
Yes.
Q, the sign of Q is non-negotiable because of nonlinear coupling. G is material dependent.
Yes.
But L is Ising, so that can be up or down.
Very good question.
So if you trained L, you could reverse M.
No.
What?
Yeah. This also confused us for a while. But there's so if I rephrase your question, maybe the question is this: L should have domains. Okay? There should be parts where L is up and L is down, right? So one expects that when you pump this thing because of this, right, you should find magnetization with different signs, right? That's the expectation.
Maybe.
But it turns out that the sign of Q is actually linked to the sign of L for the following reason. This thing here, when you think of the L, the neighboring plane, if this is upspin, the neighboring plane is downspin, okay? And this Q is a Raman active mode, and it actually should be even under inversion. So if you go to the other domain where L changes sign, Q also changes sign, okay? So the sign of Q dependent on L times Q sign is fixed. There are no domains. We looked experimentally. Many samples, there were never a domain, right? And the reason is this.